Take a long plastic ruler and flick it hard. It will bend downward as though it is about to break. Now imagine that ruler is 8 meters long and even thinner. Then give it the task of lifting a helicopter weighing several tons into the sky. It sounds impossible, but stand beside a parked helicopter and you will see something almost identical. Long, slender rotor blades, sagging slightly under their own weight. They do not look like something capable of pulling an entire block of metal off the ground. Yet when the engine roars, those seemingly fragile bars begin to spin, stretch outward, change their angle, and become the most important part of the flying machine. Without them, what is keeping a helicopter in the air? Welcome to Everyday Things Explained.
Not a giant fan. Many people think helicopters rise because their rotors blow air toward the ground. That is true, but not enough. Look closely at a helicopter blade, and you will see that it is not flat like an electric fan blade. Its cross-section resembles an aircraft wing, curved and streamlined, allowing air to flow over it and create lift. A commercial aircraft must race along a runway to force air over its wings. A helicopter does the opposite. It makes its own blades run in a circle. As the rotor spins, its blades sweep out an invisible disc above the head. It is a circular runway, creating itself anywhere the helicopter takes off. A small angle, a huge lift. But a helicopter does not fly simply by spinning faster. Its secret lies in the blade's pitch angle. Imagine holding your hand outside a car window. If you keep your hand level, the wind glides past quite smoothly, but tilt it upward just slightly, and your hand is immediately thrown upward. A helicopter blade works the same way. When the pilot pulls the control, every blade changes its pitch angle together. Even a tiny adjustment makes them bite more air, creating greater lift, and pulling the aircraft upward. A machine weighing several tons is lifted by hundreds of tiny adjustments every minute. An invention born from flips. Back in the 1920s, aviation had reached a dead end. Early engineers kept trying to bolt rigid steel rotor blades directly onto a spinning shaft. The result? The moment they took off and moved forward, they flipped over and shattered apart. Why? When flying forward, the blade sweeping ahead meets the air head-on, producing extremely powerful lift. At the same time, the blade sweeping backward loses airflow and loses its lift. One side lifts strongly, the other weakly, and the machine is bound to turn over. The historic turning point came in 1923, when engineer Juan de la Cierva, who developed the autogyro, introduced one crucial change, allowing rotor blades to flap upward and downward through hinged joints. A blade under excessive force could rise by itself to reduce the load. A weaker blade could drop down to regain its lift. It sounded like a small invention, but it opened the way for the modern rotor. The limit at the blade tip. If rotor blades create lift so well, why not simply make them spin faster? Because the blade tip is the most dangerous area. It travels the farthest distance in every rotation, so it reaches the highest speed. When the blade tip approaches the speed of sound, the air becomes heavily compressed. Drag rises sharply, vibrations appear, the noise grows louder, and lifting efficiency can fall. A helicopter therefore lives within a narrow limit, fast enough to lift tons of metal, but not so fast that it destroys its own stability. Something that looks weak, but is not. Look again at the blade sagging while the helicopter is still. It was not designed to remain motionless and rigid. It was born to spin. When it spins, centrifugal force stretches it outward, it changes angle to create lift, and moves slightly to maintain balance. It carries the entire machine not because it looks invincible, but because it knows how to move in the right way. Sometimes, what keeps something from breaking is not becoming more rigid, but being flexible enough to adapt to the force pulling on it. See you in the next video on Everyday Things Explained.